Hello, my name is Mark Worth, and I'm creating this series of videos as a resource for people looking for an intuitive and relatively complete explanation of the core ideas needed to start doing full stack development with Java. I'm going to be putting a lot of focus on overall vocabulary to make sure there is as little undefined terminology as possible. So the videos will start with building up vocabulary and then should have a further explanation and demonstration for those ideas which can be directly visualized. With that said, let's get started with some vocabulary. Binary is the smallest representation of data for computers, and all code eventually reduces to binary instructions for the machine which is running that code. Machine code is a set of machine-specific instructions which convert to binary instructions which the CPU can execute. Assembly is the first level of abstraction for programming independent of a specific machine. It's what's known as a low-level language, which lets us write code that can move around in memory and modify memory values to perform math operations or similar types of work. Compiling and interpreting are features of high-level languages, which are similar to low-level languages, but allow us to write more human-readable and complex code, which can still be translated into machine code. The difference between compiling and interpreting is that a language that relies only on compiling can take files and convert them into machine code, which can be directly executed, whereas a language which relies on interpreting will translate each instruction when the program is run, which is known as runtime. Compiled code will run faster since the translation has already been done, but interpreted code will run on a wider variety of machines as the translation happens on the machine at runtime. Java uses compilation to create what is called bytecode, which is then interpreted at runtime by the JVM, which is the Java virtual machine, which will interpret bytecode into machine code for a given machine. These definitions can definitely sound complicated right now, but I wanted to have a complete definition that gives the full scope of what we're talking about, and then to discuss some ways to visualize and memorize that information. Binary is simple enough. It's just another way to represent numbers similar to decimals, which we use every day. And before the end of this video, we'll discuss all the fundamentals you'll need for converting to and from binary. Machine code is best to think of as a dialect, as dialects can vary widely but still tend to follow the same overall rules of language. The best way to visualize assembly is as a language. The information, generally speaking, can be translated into any dialect to fit what might be needed, but the general rules of the language unify all those dialects. For compiling, it would be best to think of it as translating a written page onto another written page in a different language for someone to read later, whereas for interpreting, it would be more like reading the page and translating as you go. So now it's time to talk about how we can convert to and from binary. As for development, we really need to know this as a foundation in order to discuss how much data is stored and how much space data will take up when a program is being run, which is a fairly common task in development. So binary is what is called a base 2 counting system, whereas the everyday counting system we use is base 10. The meaning of this is that for every number in a value we write, it's being multiplied by some factor of the base. So what does this mean? Well, when learning how to count, you worked with the tens place and hundreds place and thousands place and so on. But the difference between each of these places is that they differ by a factor of 10, which, as we said, is the base for our counting system. So the best way to understand these places is in terms of the number of times we multiply that number by the base when finding the total number. This is what is called exponentiation, and we say that we raise the base to the power. But this just means that we're multiplying the base by itself, the number of times stated in the power. So now we just need to know what power we can use to represent each place, and we'll have a full idea of what our base system really means. So for example, the ones place has no factors of 10 since the number is just whatever is shown there. So we could say that the ones place has 0 powers of 10. Now, if we look at the tens place, the real number there is the shown number multiplied by 10. So there's one factor of 10. So we can see a pattern here now, right? The number of factors of 10 goes up by 1 each time we go to the left. So similarly, if we go to the right, the power of 10 goes down by 1 each time. So what happens when we cross the decimal point? Well, we're reducing the power by 1, so it goes from 0 to -1. And this makes sense because we call the first place to the right of the decimal point the tenths place. So a power of -1 means that we're dividing the number by a factor of 10. Similarly, a power of -2 for the second place would indicate that we're dividing by 2 factors of 10, or in other words, we're dividing by 100. So now that we've established these rules for exponents and understand what they mean in base 10, let's talk about base 2. So similarly to base 10, the first position to the left of the decimal is represented with 0 factors of our base. So numbers here are only multiplied by 1, so we could still call this the ones place. For the second position, which in base 10 was the tens place, we now have 1 factor of the base. So we can call this new position the twos place. And the next position could be the fours place, and so on, increasing by a multiple of 2 for each position we move to the left. Similarly, we could call positions to the right of the point the halves place and fourths place, and so on. So now the only thing we have left to discuss is what numbers can we put in these places? Well, for base 10, we can use 0 through 9, and if we add another 1, then we have to carry over because the number is added up to 10. So similarly, our limit for binary would be 1, as if we added 1, we would have the value of the base, so that would have to go to the next place. So now as an exercise, let's convert one number from base 10 into base 2, and one from base 2 into base 10. For base 10, we'll use 27, and for base 2, we'll use 1101.1. So let's start with 27. So to convert this, we'll need to know the highest multiple of 2, which is lower than 27, which in this case is 16. 32 would be the next multiple, and it is too high. So 16 is 2 to the 4th power, and we can represent that with a 1 in the 5th position to the left of the point. Now we have 27 minus 16, which is 11 remaining, and we can remove 8 from that, and then place it into the 4th position. Now we have 3 remaining, which is 2 plus 1, so we can put a 1 in the 1st position and 2nd position to the left of this point, and we're done. Now let's look at the binary problem. The 4th position represents 2 to the 3rd, so we can just multiply it by 8. Now the 3rd position, which is 2 to the 2nd, so 4. Then the 1st position, which is 2 to the 0, so 1. And lastly, 2 to the -1, which is 1/2. We can add these up for a total of 13 and 1/2. So that's the basic introduction for how code is generally run to give you an idea of how Java compiles and runs, and hopefully give some scope as to why we would want to know binary in addition to the basics of binary to help lay the foundations to understand upcoming data types. In the next video, I'll be going over data types and the basics of Java classes and object-oriented programming. In addition, I've placed a link in the description for a guide to set up Java in Eclipse, which will be needed to follow along with that video. I hope this video has been helpful.